Jai Hind to all. My name is Divya Sharma. Now, my today's video lecture is on applications of Gauss law. Now, it was covered in the previous lecture that what do you mean by Gauss law? According to Gauss law, the total electric flux through any closed surface is equal to total charge enclosed by the surface, and its final formula is rho v is equal to del dot d. So this is known as Gauss law. This is the first of the 4 Maxwell equation. Now today we will cover application of Gauss law to calculate electric field. Now Gaussian surface, it may be imaginary, symmetric, closed, hollow surface, and it is classified into 3 types: point charge, line charge, surface charge. If we are considering point charge, let us consider an example of hollow sphere, and the line charge, hollow cylinder with the top bottom closed. Means if you are considering the case of hollow cylinder, its top and bottom it should be closed. Now the surface charge, when we are considering the case of surface charge, you can take an example of hollow cube. Now it was covered in the previous lecture that closed integral d dot ds is equal to q enclosed. It means charge inside the surface or volume. Now here that is equal to integration rho L dl for line integral. For surface integral, it is integration rho s ds. If we are considering the case of volume, then integration rho v dv. Now ds is your Gaussian surface, and only those portion which contains the charge. So we have to consider it. Now application of Gauss law, first is point charge. Suppose a point charge is located at the origin. Let it be, this is your sphere, this is origin, and charge is q on this point at origin. And here is a point P, considering here point P, and electric flux. You have to determine the electric flux at this point P. Now here choose a spherical surface containing P. D is everywhere normal to the Gaussian surface. If your this is your charge, this is your point, so you have to consider here electric field in this direction, and if your unit vector also in this direction, then you have to take cos theta is equal to 1. Now here electric field due to point charge. Now here closed integration d dot ds is equal to q. Q is your enclosed charge inside the surface. Now here first write down d. D vector is equal to what? dr, unit vector of r, and ds is means you have to consider the surface of sphere. Now this is your surface of sphere. Here there is a point and charge is on this point is q. Now here this is an electric field direction, and here this is your point, let it be, this is P point, and radius in between these 2 points is represented by capital R. Now here electric flux is equal to dr, unit vector of r, and this is your Gaussian surface. Now here put all these values of d and ds. Now d is equal to what? D is dr, unit vector of r, and ds you have to find out ds according to the dl of sphere. Now you all know, it was covered in the previous lecture, that dl is equal to dl for sphere. So dl is equal to dr, unit vector of r, plus r d theta, unit vector of theta, r sin theta d phi, and unit vector of phi. So this is your dl. Now here write down the surface for unit vector r. If you are considering the case of unit vector r, then you have to multiply this and this, means r d theta into r sin theta. So you have to multiply this and its unit vector theta and d phi and d phi. Okay. So this is your surface ds, means Gaussian surface is r square sin theta d phi, unit vector of r. Now is equal to what? Enclosed charge. The enclosed charge is here q. Now multiply this and this, means here unit vector r, unit vector of r, it means dot product of unit vector. If you have same unit vector, then you can take a dot product, that is equal to 1. So here you will get here dr dot r square sin theta d phi is equal to q. Now here if your electric field is also in this direction and your unit vector is also same, means both have radial direction, same direction, then you can take dr is constant at every point. If you are considering this point, then radius is same here, and this d is also constant here at this point. If you are considering this point, means all these points, at all these points your d is constant. So dr you can take common, means outside this integration, and now here you can integrate this portion, and that is equal to q. Now here put the value of r. R is equal to what? Capital R. So put r is equal to, small r is equal to capital R. Now here dr already it is outside. Now r square you can take common, and you can integrate with respect of theta and phi. If you are integrating phi, then your limits are 0 to 2 pi. If you are integrating d theta, then take limit 0 to pi, and that is equal to 0. Now integrate it and put all these values, and you will get the dr is equal to 1 upon 4 pi q upon r square. If you are taking vector of d, then 1 upon 4 pi q upon r square unit vector of r. Now if you want to draw a graph in between small r and this magnitude d, then you have a graph in decreasing, means linearly decreasing in order. It means here by this formula you can check your d vector is inversely proportional to 1 upon r square. So you can draw a graph in between d and r. Now second is infinite line charge. If you are considering the case of infinite line charge, then you have to determine d at the point P. Let us consider you have a cylindrical surface. You are considering here length of cylinder is L, or you can consider it as H. Now you have to determine d at point P. So this, let it be, this is your point P on this cylinder, and you have to find out flux on this point. You have to determine the d at this point. Now here d is normal to side surface, doesn't exist on the top and bottom surface. While you are calculating top surface, while you are calculating d for top surface, bottom surface and the curved surface, so top and bottom it should be closed. Now here let it be, this is your figure, this is your line charge on this cylindrical, this is your cylindrical surface, and charge are uniformly distributed on this line. This is and charge on this line is represented by lambda, and this is the rho. Rho is same in all points. Now rho is constant. Now height of this cylinder is represented by h. Now here d is equal to d rho unit vector of rho. Now here apply here Gauss law. So Gauss law is equal to, means enclosed integration d dot ds is equal to q enclosed. So you have to take enclosed charge, and enclosed charge for this cylindrical is in integration lambda dl. Lambda is your charge density on this surface, and dl, you are taking dl height of the cylinder, so it is represented by h. So you will get here lambda h. Now calculate it. You have to calculate this d dot ds for top, bottom and closed, top, bottom and curved part. Now for top you are writing here d, you have to write down d and dot ds. So first you have to calculate ds for the top. So if you are considering top, it is your z axis. Now here for unit vector of z, you can you should know dl for cylindrical is equal to what? D rho unit vector of rho plus rho d phi unit vector of phi and dz unit vector of z. Now here if you are considering the case of unit vector of z, then you have to multiply d rho into rho d phi and unit vector of rho and phi. So it means if you are considering the case of z, so you have to multiply rho d phi and unit vector of z. Now here this is your d in form of rho. So d rho unit vector of rho. Now you are taking dot product of this and this, so you will get here 0. Now here calculate for the bottom case. So again you have to take your, this is your z axis, so unit vector of z at the top is in positive form, but here at the bottom side you have to take it in negative form. Now here write down ds. So ds again, if you are considering the case of unit vector of z, so multiply rho d phi. So this is your ds, and you all know d is what? You can write down d rho a rho. Now here if you are multiplying these unit vector, then you will get here 0. Now the third case you have to calculate for the third case, that is curve. Now here for curve d rho, a unit vector of rho. Now here in the third case, means if you are considering the case of third, means curved part, so here you can see your rho is constant here. If you have constant rho, then you have to take surface. It means what? It means you are considering the case of unit vector of rho. So you have to multiply rho d phi and dz. So write down ds is equal to what? Rho d phi dz. And you all know d, value of d is d rho unit vector of rho. Now here you have unit vector of rho, here is also unit vector of rho. So if same unit vector, then you can take a dot product of this, and that is equal to what? That is equal to 1. Let it be a rho, this is unit vector, dot product of a rho, unit vector of this is equal to 1. So put the value here 1, and you will get here d rho dot rho d phi dz. Now here d rho you can take common, rho is also you can take common, because we don't have differential part of rho. So you can integrate it part of d phi and dz. You will get here finally you will get d rho 2 pi h. So this is the output for this d dot ds. Now here d dot ds is equal to what? Lambda h. Now put the value of for top, bottom and the curved part. So curved part is d rho 2 pi rho h is equal to lambda h. So from this equation you can find out d rho is equal to lambda upon 2 pi rho. Now this is d rho. Now here if you want to take a vector of d, that is equal to what? Lambda upon 2 pi rho unit vector of rho. Now another for infinite sheet charge, now you have to determine here d at point P. Let us choose this is a rectangular box with top and bottom area, and area is represented by A. Now here d is normal to the top and bottom and does not exist on the side surface. Now here this is your infinite sheet of charge, and it is represented by rho s, and its units are coulomb per meter square. And this is your P point on this rectangular box, and its electric flux density is representing by d vector. Now this is your electric field in this direction. Now here you have to calculate, again you have to calculate d electric flux density for this rectangular box. Now here you all know Q is equal to what? This is your, if you are considering this surface, rectangular surface, now here Q is equal to rho s in integration ds. Now here that is equal to what? Q is equal to d dot ds. Now here dz you can take common d, as d is same at all points if you are considering on this surface. So you can take dz as a common, and you have to take close integration of ds. Now here write down ds in form of top and bottom. So calculate ds for top and bottom, you will get here A and A. Means because here you are considering area is represented by A. Now here put the value for top and surface and bottom surface A plus A, and here your ds for this charge is equal to what? At this point is also equal to A. Now find out ds is equal to what? ds is equal to rho s upon 2. Here you can calculate electric flux density, that is equal to what? Rho s upon 2 unit vector of z. And if you want to find out electric field intensity, that is equal to what? That is equal to rho s upon 2 epsilon naught unit vector of z. Now uniform charged sphere. A sphere of, this is your sphere of radius A, and has a uniform charge density. Its uniform charge density is represented by rho v. What is now here? What is the direction and magnitude of electric field everywhere? Now here you have to determine electric flux density. Let us construct Gaussian surface for cases. Now here you have to take two cases. First case is R is less than or equal to A, and second case is R is greater than or equal to A. Now here in this case your R is less than A, and here in this case R is greater than A. So you have to consider these two cases. Clearly, all directions are created equal in this problem. The electric field will point away from the surface at all points, and electric field must depend only on the distance. Now first case. Now here first case is R is less than or equal to A. When we are calculating flux for this Gaussian surface, only include electric charges inside this surface. Here enclosed charge is represented by Q, and that is equal to what? Rho V dV, and you can take rho V as a common, means outside this integration, because rho V is constant for all this Gaussian surface, and you have to take the integration of volume. Now for integration of volume, you should know dl for sphere. So dl for sphere is dr unit vector of r plus r d theta unit vector of theta plus r sin theta d phi unit vector of phi. So with this dl equation, you can find out here dv. dv is what? dr dot r d theta dot r sin theta d phi. So write down here, this is the dv, r square sin theta dr d theta d phi. Now take limits of r theta phi. R limits are 0 to r, theta limits are 0 to pi, and phi limits are 0 to 2 pi. As already we have done in the first unit, and in this video lecture already, in that video lecture already covered how to write down dv and limits of this dv. Now here you will get, while you are solving this equation, Q enclosed is equal to rho V dV. So here you can put the value of dV here in this form, and you can find out enclosed charge, that is equal to rho V 4 upon 3 pi r cube. Now total flux on this surface. Total flux on this surface is equal to what? Closed integration d dot ds. Now here d you can take common, means you can take outside this integration and put the value of ds. Now here while you are putting the value of ds, so you can write down ds with the help of this dl, r square sin theta d theta and d phi, if you are considering the case of unit vector of r. Okay, now flux, while we are putting all these values and you are integrating, this theta is equal to 0 to pi and phi is equal to 0 to 2 pi. So you can put all these values and integrate it and find out the total flux, that is equal to what? dr 4 pi r square. Now as you all know from the Gaussian law, your charge enclosed is equal to what? Enclosed integration d dot ds. So put all these values, means this equation and this one, equation 1 and 2, you can write down, both are equal to each other. Now while you are putting all these values, and you can find out d, means electric flux density, that is equal to what? r upon 3 rho v unit vector of r. This is the final d. Now the second case, when r is greater than a. Now you are considering the case when r is greater than a. This is your radius a, and this is radius is represented by a. Now here find out electric flux density, that is d. Now the charge enclosed in this case is the entire charge. Now here that is equal to what? Integration rho v dv. Now put here the value of dv as we had done in the previous slide, how to find out r square sin theta dr d theta d phi. Now take the limits of r, theta and phi. R is equal to what? 0 to a, and theta is equal to 0 to pi, and phi is equal to 0 to 2 pi. Now put all these values and you can find out enclosed charge, that is equal to rho v 4 upon 3 pi a cube. While we have to calculate flux, flux is equal to what? Enclosed integration d dot ds. So d you can take common, means outside this integration, and write down the value of ds. So write down the value of ds according to this surface. Write down r square sin theta d theta d phi, and units for theta is equal to 0 to pi, and units for phi is equal to 0 to 2 pi. So you can integrate it with respect to theta and phi and find out flux is equal to what? dr 4 pi r square. Now this is your enclosed charge and this is your flux. So you can write down the value flux is equal to q enclosed and put this value, this one, this equation 1, this equation 2, equation 1 and equation 2 are equal. So write down here all these values and find out dr, that is equal to what? A cube upon 3 r square rho v. Now if you want to find out unit vector of d, so that is equal to a cube 3 r square rho v unit vector of r. So this is the charge for uniformly charged sphere, means you have to find out here electric flux density for this uniformly charged sphere. Now from the previous slides, as we have done how to find out d for when you have r is less than a and r is greater than a and r is less than a. If r is greater than a, your d is equal to what? Rho v a cube upon 3 r square unit vector of r, and when r is less than a, your d is equal to what? R upon 3 rho v unit vector of r. So how to draw it in a graph? Now take, this is your x-axis, and this is your y-axis. Now here when r is less than a, when r is less than a, so here this is your point A. So write down here r, this is the linear graph. Here r, its value is r upon 3 rho v when r is greater than a. So write down here for this electric flux density is equal to what here at this portion? A cube upon 3 r square rho v. Now next is electric potential. Suppose we have a point charge q from a point A to B. Let us consider this is your origin, this is your electric field lines. Now here there is a line A to B, and A to origin its distance is RA and origin to B its distance is RB. Let us consider our differential length on this line AB, that is DL, and distance from origin to this DL is represented by R. Now here find out, you have to find out the electric potential on this surface. Now here you have a point charge q from point A to B in this electric field A. Apply here Coulomb's law, and Coulomb's law, the force on q charge is equal to what? Force F is equal to QE. Now here work done in displacing the charge by dl is equal to what? dw is equal to minus f dot dl. Now here put the value for f, that is minus q charge, this is your charge electric field intensity dot dl. So put the value of f is equal to what? QE, and you will get this dw. Now negative charge indicates that work is done by the external agent. Now total work done, or you can say potential energy here while you are moving from A to B, then W is equal to what? W is equal to minus Q, and you have to integrate it with respect to A to B. So your integration lower limit is A, higher limit is B, and you have to integrate this electric field dot dl. Now dividing W, you can divide it by Q, then you will get the potential difference in between point A and B. That is equal to what? W upon Q is equal to minus A to B integration A to B E dot dl. Now here this is your potential difference in between points A to B. Now electric field in this figure due to point charge q located at the origin is equal to what? E is equal to q upon 4 pi epsilon naught r square unit vector of r. Now from this equation D, as we have done, D is equal to what? This is VAB is equal to minus A to B E dot dl. So put the value of E here, and E is equal to what? Q upon 4 pi epsilon naught r square unit vector of r. So put this value here and you will get Q VAB is equal to minus R integration RA to RB Q upon 4 pi epsilon naught r square unit vector of r dr unit vector of r. Now you can integrate it while you are putting the value of integration also RA to RB. You will get here VAB is equal to Q upon 4 pi epsilon naught in bracket 1 upon RB minus 1 upon RA. Now potential difference in between point A to B is equal to what? VB minus VA. So VB minus VA are the potentials at point A, B and A respectively, and potential difference may be regarded as the potential at B with reference to A. And if VA is equal to 0 as RA tends to 0 in equation D, and potential at any point RB tends to R due to point charge Q located at the origin, V is equal to Q upon 4 pi epsilon naught R. So this is the potential at any point, or you can say potential difference between that point A and B Now here the potential at any point is the potential difference between that point and a chosen point at which the potential is equal to 0. Now here, by assuming 0 potential at infinity, the potential at a distance r from a point charge is the work done per unit charge by an external agent in transferring a test charge from infinity to that point, and that is V is equal to what? Minus infinity in integration, and integration limits are infinity to r E dot dl. So this is the potential difference. Now thank you.